Before we get into answers, let's do the usual pre-analysis. And if I go back to my pre-analysis framework, the first thing to think about is the mathematical model. And to do that, one has to think about what is the Reynolds number. And in fact, for most fluid flow problems, it's a good idea to think about what is the Reynolds number because it has implications for what the flow is going to do, as we will see in this particular case. Here, the Reynolds number is defined this way, and it comes out to be 6 million. So this is the density and viscosity of the flow, which we know. You need a length scale in the Reynolds number, and what's used is the chord of the airfoil. If that's my airfoil, and that's the leading edge, and that's the trailing edge, then the distance from the leading edge to the trailing edge is the chord length. So if I take that distance, that's conventionally the length scale used in the Reynolds number. And you also need a velocity scale in the Reynolds number, and what's used is the so-called free stream velocity. We have the flow coming in at an angle called the angle of attack. So the free stream velocity is the velocity far upstream of the airfoil. And we're looking at this, in a frame of reference, moving with the airfoil. So the flow is coming and coming in, and the airfoil is not moving in that frame of reference. Flow is turbulent for airfoils at this Reynolds number. That's a Reynolds number of 6 million, above a Reynolds number of 100,000 to 500,000, depending on the circumstances. You're going to get turbulent flow. So this is well above 500,000. So this is a fully turbulent flow. What is the implication of that? The turbulent flow is fluctuating. You get fluctuations in velocity and pressure, but those fluctuations are not about the laminar or the non-turbulent solution. So if I go to any particular point in the flow and I track, let's say, the velocity u versus time, I'll see something like this. I'll see a random variation in time with significant variations. But if I average over time, that average is not varying with time. In fact, this particular case would be called a statistically stationary turbulent flow. And I can decompose the velocity into this average here and a fluctuation. This is called Reynolds decomposition, and this average would be called a Reynolds averaged velocity. Here is a figure from the ANSYS documentation, used courtesy of ANSYS. So if and this is for a backward facing step, which is a canonical turbulent flow. And if I plot an instantaneous contour of the velocity itself, so if I go to some particular time here and I plot a contour of the velocity, I'm going to see, lots of details and structures like the small scale structures and so on. So that's contour of u. And instead, if I plot contours of the Reynolds average, I'm going to see something like that. You can see that this is, much smoother and much more, much better behaved than this. In most engineering problems, you can calculate only the Reynolds averaged velocity and pressure, and that's what we're going to do in this particular case study. So we'll calculate the Reynolds average velocity, and we'll calculate the Reynolds average pressure. We need to see how the governing equations are modified when we need to solve for the Reynolds average quantities. We look at the continuity equation first, and then we look at the momentum or the Navier-Stokes equations.